Next unit is work, heat and the first law of thermodynamics. We can start by discussing the concept of work. The term work is known to us from the topic of mechanics. And normally we are saying that work is said to be done when the point of application of the force displaces. If a system undergoes a displacement under the action of force, work is said to be done. The amount of work is equal to the product of the force and the component of the displacement parallel to the force. If a system as a whole exerts a force on its surroundings and a displacement takes place, the work that is done either by the system or on the system is called external work. Example is expansion and compression of a gas enclosed in a cylinder with a piston. Here you can see the examples. This is, and now we are introducing the sign for work as either positive or negative, depending on either work is done on the system or by the system. When work is done by the system, it is regarded as negative. And when work is done on the system, work is regarded as positive. So, when work is done on the system, work is regarded as positive. Here you can see that this is work done on the system means it is compression. So, this is a gas contained in a cylinder with a movable piston. Initially, the piston is here. The position of piston is here. You can see it by a dotted line. And then it is pressed to this point. That means compressed. And here, this is the initial position. And it has been expanded. That means work done by the system and you are regarding it as negative. So work is done by the system as work is done on the system as positive and work is done by the system as negative. The work done by one part of the system or other part is called internal work. In the macroscopic thermodynamics, internal work is not significant. We consider only the external work. So, unless otherwise indicated, work means external work. So, in our initial topics, we are dealing with the thermodynamics or macroscopic concepts. So, we are always considering the external work. Now, we will derive an expression for work done in changing the volume of a hydrostatic system. We have already defined the term what is a hydrostatic system. So, you may consider a hydrostatic system contained in a closed cylinder. This is the closed cylinder equipped with a frictionless movable piston. This is the movable piston. And as you know, this is the adiabatic walls. So, there is no possibility of transfer of heat to the system. That is, you can regard this as this is undergoing under adiabatic conditions. So, it is a, let A be the cross-sectional area of the cylinder and P be the pressure exerted by the hydrostatic system on the piston face. So, this system has a pressure P and this A is the area of cross-section. So, you can see that always pressure is force by area, or force you can write as pressure into area. So, a force of P into A is acting here by the system. That means on the If by application of a force, if you are trying to move this piston, you have to apply an applied force which should be just greater than this PA. Or theoretically you can say that when you are applying a pressure P into A to this side, you can move that piston. So the gas is compressed by an external force F. Then F equals minus PA. This applied force will be equal and opposite to PA. And by the application of the force, you can see that initially the piston is here. It has moved through a distance dx. The work done on the system during the quasi-static processes, you are writing as just work done dW equal to force into displacement. And the force you are writing as minus PA dx. And this A into dx you can write as P into minus P into dV. Here, this is the area and this is the length. So, this A into dx is the volume of this portion. So, that A into dx you are writing as the volume. So, dW equal to minus PD. And when the volume changes from an initial volume VI to a final volume VF, you can write the work done as W equal to minus integral VI to VF PdV. The presence of minus sign before PdV ensures that a negative dV, a compression, gives rise to a positive work on the system, and a positive dV, expansion, yields negative work done by the system. Again, you can see that this is the expression. So, always you are taking this dV as change in volume, and always change is final minus initial. It means final volume minus initial volume. And in compression, final volume is less than initial volume. So, final minus initial is a negative quantity. So, this dV will be a negative quantity. So, you have two negatives. That means P minus PdV will be a positive quantity. That means work done on the system. And during expansion, dV, that means final volume minus initial volume. Final volume will be greater than initial volume during expansion. So, final volume minus initial volume is a positive quantity. So, dV is positive. So, minus PdV will be or work done will be a negative quantity. And next is PV diagram and work done. We have already discussed this concept of PV diagram. In a PV diagram, work done can be represented as the area enclosed by the PV diagram. We know that in the PV diagram, we are plotting pressure on y-axis and volume on x-axis, and it was also known as the indicator diagram. In a cyclic process, the net work done is the area enclosed by the cyclic curve. Here you can see this is the PV diagram. PV diagram of a gas with a shaded area to show work done by the system or work done on the system. And this first curve is for expansion. You can see the arrow mark. Volume is increasing from here to here, so it is expansion. And we are considering work done as area under the curve. That you can prove it very easily. You just see this. So, if you are taking a very small portion here, a line which may be parallel to here, very small. So, during that region or during that this portion, you can consider pressure as almost constant. So, this side will be P and this side will be D. So this P into dV will be area of such a small strip. This will be a small strip. And according to our expression, PdV or minus PdV is the work done. That is why you are considering this as area under the curve. And in order to find the total work done, you have to integrate that. So this will give you the area. And you know that this is an expansion process. So work done will be negative quantity, and this is compression from here to here. Actually, it is going from the state F to I. And this is a cyclic process. And in cyclic process, here we have represented it with a cyclic process. That means a closed integral from I to F and from F to I. So during this process, work done is given by area enclosed by this loop. So here you can see that from I to F and from F to I, the system is not coming back to initial conditions through the same path, but it is a cyclic process. So during this process and during this process, area under the curve is not same. That means work done is not same, which means that you can have an idea that work depends on path, and that idea we will discuss elaborately here. Dependence of hydrostatic work on path. Let a system at an initial equilibrium state I, here it is I, characterized by the coordinates Pi, Vi, Ti, initial pressure Pi, initial volume Vi, initial temperature Ti, is taken to a final equilibrium state F, this is F, with the coordinates Pf, Vf, Tf. Pf final volume, Pf final pressure, Vf final volume, and Tf final temperature. And you are considering this initial pressure Pi as 2P0 here, and this final as 2V0. There are many ways in which the system may expand from I to F. Now we consider three different paths: IAF, IBF, and straight path IF. IAF, IBF, and IF. So in this IBF and IAF, first is an isobaric process IAF, then an isochoric process. Isobaric means constant pressure, then constant volume. IBF means first you have an isochoric process followed by an isobaric process, and this is some type of process IF. The path IAF consists of an isobaric process followed by an isochoric process. The work done in the path is, you see this, what is the work done during this path? Area under the curve IAF is isochoric. So this is the area enclosed by, that means it's point IA, this 2V0, V0. It is the area enclosed by this rectangle. For a rectangle, we can find the area as length into breadth. And this is 2V0 and this is V0. So this is 2V0 minus V0, that is V0. And here, this is 2P0 and this is 0. So it is 2P0. So the work done will be actually 2P0 into V0. That is the area. And normally work done you have to consider as minus PdV. So you are considering it as minus 2P0 V0. So 2P0 into V0. For the second path IBF, first isochoric, then isobaric. And here no area under the curve. So you have to consider only this portion, this BF. So this is the work done during the path IBF, that you can take as, this is same as 2V0 minus V0, that is V0, and this is P0 minus, and this point is 0. So here work done is minus P0 V0. And for the straight line path, that means this one, I to F directly, this is the case. So simply you can consider this as, it is a rectangle plus a triangle, and this area we have already calculated as P0 V0, and this is a triangle whose area you can write as half BH. So this is half into, this is say 2P0 minus P0 is P0, 2V0 minus V0 is V0, so half P0 V0, and this is P0 V0. So P0 V0 plus half P0 V0 will get as 3 by 2 P0 V0. So from I to F, we have considered 3 different paths, and during these 3 different paths, work done is not same. That means you can say that work done depends on the path. These calculations show that the work done in taking the system from an initial stage to a final stage depends not only on the initial and final states, but also on the path along which the system is taken. That means the path integration. So the infinitesimal thermodynamic work does not depend upon the thermodynamic coordinates P, V and T. That means it is not depending on the intermediate coordinates. Therefore, it is an inexact differential, and it is denoted as d bar W. We have to consider this as, or read this as d bar W. Here we have put a bar. It is like your H cross. So work depend on the path. A path dependent quantity you are normally considering as inexact differential, and writing like this. The thermodynamic work is not a state function, since the integral minus integral PdV is path dependent. So it is not a state function. State function means that function is depending only on the initial and final coordinates. Like your if you are considering the gravitational work done or electrostatic work done depend on the initial and final points only, not on the path followed. You are considering them as the state functions. But here, thermodynamic work done depends on the path followed. So you are considering it as path dependent function. And this is the way of writing your d bar W. Writing d, here you have to put a cross, like your H cross. So this is d bar W. And now we have different processes like isothermal, isobaric, isochoric, adiabatic, etc. We will be calculating the expression for work done during these type of quasi-static processes. First we will start with the isothermal work. An isothermal process is a process during which the system is in good thermal contact with the surroundings so that temperature remains constant. Our general expression W as minus integral Vi to Vf PdV. The equation of state of an ideal gas you can write as PV equal to nRT, or this P you can write that nRT by V, where N and R are constants. Substituting for P, that means substituting this P as nRT by V, W equal to minus integral Vi to Vf nRT by V d. this R and N are constants, normally constants. And for isothermal process, this T is also constants. So you can take this nRT or they can be considered as constant and taken outside the integral. So W equal to minus nRT integral Vi to Vf dV by V. And the integration can be performed to yield this integral dV by V. You can take as log natural V within limits Vi to Vf, and log natural V limits Vi to Vf can be written as log natural Vf minus log natural Vi, and log A minus B you can write as log of A by B. So it is log natural Vf by Vi. W equal to minus nRT log natural Vf by Vi. This is the expression for work done during isothermal process. Here also you can see that if Vf is greater than Vi, log natural Vf by Vi is a positive quantity, work done is negative. And if Vf is less than Vi, this will be a negative quantity, so work done will be positive. Now adiabatic work. During adiabatic process, the system is perfectly isolated from the surroundings so that there is no heat flow between the system and the surroundings. And hence, pressure, volume, temperature of the system change. And the expression for work done as W equal to minus Vi to Vf Pd. For an adiabatic process, we have this equation is known to us. Expression for adiabatic process as PV raised to gamma equals constant, that is K. Or from this K is equal to P equal to K by V raised to gamma, or you can write it as K into V raised to minus gamma. So work done is minus integral Vi to Vf K V raised to minus gamma dV. And the integration will give you this V raised to minus gamma dV as constant K is here. V raised to minus gamma plus 1 by minus gamma plus 1 limits Vi to Vf. 1 by gamma minus 1 is constant. Again, K V raised to minus gamma plus 1 Vi to Vf. That means 1 by gamma minus 1 K Vf raised to minus gamma plus 1 minus K Vi raised to minus gamma plus 1. We have V raised to Vf minus gamma plus 1, you can write as Vf raised to minus gamma into Vf. So that is 1 by gamma minus 1 K Vf raised to minus gamma Vf minus K Vi raised to minus gamma Vi. Just we have written as, your pressure can be written as, this is the equation, pressure equal to K V raised to minus gamma. That means K Vf raised to minus gamma is the final pressure Pf. And similarly, this K Va raised to minus gamma is the initial pressure Pi. So this is 1 by gamma minus 1 Pf Vf minus Pi V. And for any ideal gas, we have PV is equal to nRT. So you can substitute this as nRTF and this as nRTI. Taking nR outside, that means you can write W as nR by gamma minus 1 into Tf minus Ti. We have mentioned that during adiabatic process, pressure, volume and temperature, all these quantities may change. So in terms of pressure and volume, work done is 1 by gamma minus 1 Pf Vf minus Pi Vi. And in terms of temperature, it is nR by gamma minus 1 Tf minus Ti. We know this gamma is Cp by Cv, which is always greater than 1. So, we know that an expansion process is work done by the system, which is a negative quantity. So, work done is negative. So, in order to have a negative quantity, clearly this Tf should be less than Ti. That means during adiabatic expansion, temperature decreases. And during compression, W is positive, so Tf should be greater than Ti. And now we have isochoric and isobaric. In an isochoric process, there is no change in the volume of the hydrostatic system. So this dV is 0. Therefore, the work done is 0. And for isobaric process, pressure remains constant. So this pressure can be taken outside the integral. Simple. So it is W is minus integral Vi to Vf P dV can be written as minus P into integral Vi to Vf dV. This is V within limits Vi to Vf, that you can write as Vf minus Vi. So it is minus P Vf minus Vi. And this P into Vf you can write as nRTF, and P into Vi can be written as nRTA. So this is minus nRTF minus Ti. And that's all about this initial topics in your work calculations. Thank you.